Okay, so I suppose I'll get started. I welcome the viewers to this problem solving and live interaction session for the subject experimental stress analysis offered by Professor K. Ramesh on the SWAYAM portal. My name is Ganesh Ramaswamy. I'm a PhD scholar in the Department of Applied Mechanics and Biomedical Engineering, working under the guidance of Professor K. Ramesh and co-guidance of Professor U. Saranan from the Civil Engineering Department. So today we'll be looking at the contents of week 6, which has to do with photoelastic calibration, fringe ordering, and the fringe thinning methodologies. So with that preamble, let us look at the first question of the day. Fringe patterns isochromatics corresponding to an angle bracket subject to a diametral load is as shown. So the question asks how many 0th fringe orders are there in the model domain shown in the figure. So we basically have a bracket like that. I'm just approximately drawing it. So we basically have a bracket like that, and then it is loaded at these points, loaded at the black points. It is loaded here, and we have been asked how many 0th fringe orders are there in the model. So let us go about looking for them. So first thing we know from our knowledge of solid mechanics, we know that at a free outward sharp corner let us say this plane is characterized by, let us say, n1, which is its normal vector, and this is characterized by n2, which is its normal vector. In fact, let me use the arrow n1 vector and let this be n2 vector. So now we know that traction vector at any surface n, the traction vector is given by the stress tensor operating over the normal vector. So this we know. Now let us say that these are free surfaces. And this is a free surface. So for surface number 1 and for surface number 2, traction at surface 1 is actually a 0 vector. Similarly, traction at surface 2 is also a 0 vector. Why? Because these are free surfaces, meaning free of traction, free of applied traction. In such a case, if we were to look at this corner, in this corner it creates an ambiguity as to where we should take the normal vector at that point. So to resolve this ambiguity, and since this is unloaded, the stress tensor at the sharp corner, to resolve the ambiguity, of which normal to take, we'll see that the stress tensor itself would be 0 at this free outward corner. So that implies that it is the stress tensor there is 0. If the stress tensor there is 0, then sigma 1 minus sigma 2 is 0, which implies that n is 0 from the stress optic law. We will have sigma 1 minus sigma 2 equal to n f sigma by h or t, howsoever we name it. H or t is basically the thickness of the specimen. So, when sigma 1 and sigma 2 are both 0, so the fringe order there would be 0. Now, let us go about identifying these points. We know that this is one point where we have a free sharp outward corner. This is another point. Similarly, this is another point. So, we have identified 3. If let us say that this was not loaded, this corner was not loaded and it was free, then we can see that the fringe order here would also be 0, but since it is loaded, it is not traction free, hence we cannot make that conclusion. So, we have already identified 3 points, namely 1, 2 and 3, where fringe order is 0. Now, let us look at some other nuances. Now, we can see that here in this case we have a fringe like that, and then another fringe like that, and then we have a blob. So, what this is telling us is, even in the case of ring, if we see, as we load it, the fringes keep accumulating at one point, but that point, the fringe order at that point, the isochromatic fringe does not disappear, only the fringes get concentrated towards that zone. That implies that it is an isotropic point. So, this point basically, this point is fringes get accumulated, fringe density, I would rather say that fringe density, fringes become dense but do not disappear. Hi, welcome. Are you able to hear me all right? Mr. Shiva Kumar?
Sir.
Yeah.
Audible, sir.
Okay, thank you. So, here the fringes become denser but do not disappear, which implies that we have a fringe order 0 over here. Very well. So, now that we know in this problem that this is fringe order 0, we know that this is fringe order 0. Now, what can be said about this red fringe? If blue is 0, then we can see that the gradient increases in this direction. So, this has to be fringe order 1. This is fringe order 1. And we know that this end is actually loaded. So, it is safe to assume that as we go near that point, the fringe orders would increase. Hence, at this point, we know that this is the direction, rather this is the direction in which the fringe order increases. Fringe order increases in this direction, which means in the opposite direction it has to decrease. In this direction, it would have to decrease. With that in mind, we know that this is fringe order, this red one is fringe order 1, hence we can conclude that this fringe order that we see at that surface is actually fringe order 0. This is actually fringe order 0. Similarly, this is actually fringe order 0. So, we have one more point here, one more point here. So, we have been able to identify basically 6 points, 1, 2, 3, 4, 5 and 6, where the fringe orders are 0. So, for fringe ordering, basically we need to know at least the fringe order at one point, and then we can go about resolving it from our knowledge of solid mechanics, from our knowledge of the features of the isochromatic fringes and other aspects to it. For example, we know where the fringe gradient is increasing or decreasing. Based on that, we can make some evaluations as to what would have been the fringe order there. Whereas, if I were to take a color image of this, I can already compare it with a standard table and find out what the fringe order is, provided the maximum fringe order there is 3, because after 3 what we generally see is the colors repeat themselves. So, it requires some additional techniques in order to find that out, but that is the subject matter of 3 fringe photoelasticity, which we will be discussing in the coming week, but I am just giving you a peek into what it entails. So, I hope that is clear. So, this is how we have done the fringe ordering. So, a similar related question, let us look at this question now. The figure shows the dark field fringe patterns corresponding to a circular tube under internal pressure. So, what we are saying is we have a tube like that. So, we have basically a tube like that where this is the material. So, we have a tube like this. Let us take it to be like that for ease of understanding. And this is subject to an internal pressure. So, we know that pressure is invariably perpendicular to the surface. So, we have pressure applied like that. And this is how the isochromatic fringe patterns look. Basically, what we are seeing here, is that they are concentric rings, and the density seems to be varying as we go about farther from the edge. And then in this we have one fringe pattern like this over here, and on that fringe pattern they have labeled 2 points, 2 red points they have labeled. Similarly, for the next fringe order they have labeled 2 yellow points over there. And if we were to project this like this, we are able to see that they meet somewhere around the center of the disc, so to speak. So, these are radial lines. It is safe to consider that these are radial lines. Okay, so with this background, let us look at what the question is asking. So, it is asking if it is possible to find out the fringe order with this given information. So, what have we been given? We have been told that this is a dark field isochromatic plot. So, this tells us that the fringe orders are integers as 0, 1, 2 and so on. So, that is the information provided by the dark field fringes corresponding to a circular tube under internal pressure. So, from the mechanics of the problem, it says that it is a circular tube. Basically, it is a thick cylinder subjected to an internal pressure. Okay. We have not been given the fringe order at any point. In such a case, we cannot find out if we were, let us say, if we were given the fringe order at this point, based on the fringe order at this point and the gradient direction, we will be able to number some other fringes. Or if we were able to see some special points such as isotropic points, then we would have been able to identify something. But this is as simple as having two concentric fringes, circular fringes, from where nothing can be gauged unless the fringe order at least one point is given. So it is not possible to find the fringe order with the given information. Okay. Which of the following statements are true for the problem given? Fringe order at the red points are higher than that at the yellow points. Fringe order at the yellow points are higher than red. Fringe order are same at both red and yellow points. Fringe order 0 at the internal boundary, at the inner boundary is what it says. So basically, when we take this problem of mechanics, and if we were to analyze a radial line like that, what we will see from the symmetry of the problem, shear stresses is 0. So there is no shear. So let us say I was to take this to be the radial direction and this to be theta the direction. What I mean is I am analyzing this in the r theta coordinate system. So at some point this will be my ER and this will be my E theta, that is what I mean. So I am analyzing this in the cylindrical polar coordinate system. So if we look at our equations, in this case actually sigma r and sigma theta or rather let me write here, for this problem of an annular cylinder subjected to internal pressure. So basically we will see that sigma r is proportional to 1 by r squared. Similarly, sigma theta will be proportional to 1 by r squared. And we know from the symmetry sigma r theta or tau r theta, in other words, tau r theta is 0 because of the axisymmetric problem. Axisymmetry. So what we are trying to say is these two are the principal stresses in themselves, because the shear at any r and theta is 0, and this shows an inverse variation with increasing r. So it is safe to say that for this problem, if I take this to be the origin, so this is r internal. So when I am analyzing at the surface, this will be r internal. When I am analyzing at the outer surface, this will be r external. So r has a variation like that. So at the internal surface, naturally r internal is less than r external for this. Therefore sigma r and sigma theta for internal is greater than sigma r and sigma theta for the external. Internal and external, I mean the inner and outer surface of the, I mean this is the internal, that is the outer external. So we can see when will this go to 0, when r tends to infinity, we can say that these stresses actually disappear. So what we are saying is this is the inner surface. If I were to take a section which is very far from the internal surface, there we can safely assume that the stresses go to 0. If that be the case, then definitely we can say that the fringe order at this point at the red point is higher than the yellow point. That we can say the fringe order is basically decreasing in this direction. So the fringe order at the red point is higher than the yellow point. The second option is just the opposite of this, so naturally that will not apply. Let us just look at the third option. It says that the fringe order is same at the yellow and at red and yellow points. Now we are able to see that this is a discernible fringe. We can clearly see that there is white on both the sides and we have a black pattern like that. Similarly, here we have a clear black pattern like that, which indicates that these are not the same fringe orders. If this was the same, let us say at black and at the red and yellow point, if the fringe orders were same, then the entire thing would be of the same color, meaning entire thing would be black. But that is not the case. Here we are able to see individual fringes. So definitely fringe order is not the same at the red and yellow points, and fringe order is 0 at the inner boundary. Now we are able to see it is subjected to some stress at the inner boundary. So naturally fringe order will not be 0 there. So this also doesn't apply. So the fringe order at the red points are higher than that of yellow points. So this is the correct answer for this. So I hope that that is clear. If there be any questions, you please feel free to ask. In the meantime, I'll move forward. So what we have in this question is a circular disc of diameter 50 mm. So we have a circular disc and this diameter is 50 mm and its thickness, meaning the out of plane thickness, is, let us call it h, that out of plane thickness is 6 mm, it is given, is compressed diametrically. So we have, let me draw the force in red, force in black. So it is compressed like that along its diameter. So this is the diameter, so it is getting compressed along its diameter with a point load of 200 newtons. So this is 200 newton, this is also 200 newton. The fringe order at the center, let me draw the center, this is nearly the center of the disc. The fringe order at the center is found to be 1. Now they are asking what is the F sigma value. Now we must note that generally for photoelasticity we need to calibrate the material so that using a known problem, so that when we go about solving for an unknown problem we know its material properties. Material property in case of photoelasticity implies whatever ties the optics to the mechanics of the problem, which happens to be F sigma in this case. Now from the stress optic law, from the stress optic law, we know sigma 1 minus sigma 2 is given by n F sigma by h, where h, I just defined the thickness of the model, n is the fringe order, F is called the material stress fringe value, which has a units of Newton per mm per fringe, and that is what is asked for this problem. So we have this equation at our disposal. On the right side, fringe order n is given, the thickness of the specimen is given to be 6, fringe order is given to be 1, F sigma is what is asked. So from the left side we have to evaluate sigma 1 minus sigma 2. Now we know that sigma 1 minus sigma 2 is dependent on the problem at hand, and this happens to be a problem of a disc under diametral compression, and this also has a spatial variation. Sigma 1 minus sigma 2 will vary as the point depending on which point we consider, and we have been told that we are considering the center point for this purpose. So for a disk under diametral compression, from the equations, if you see, it will be actually sigma x, sigma y and tau xy will be a function of x and y and the other loading parameters. Now in that x and y, we just need to plug in x equal to 0, y equal to 0. Why? Because our origin is set here at the center, and that is the point we are actually considering. So when we plug that, what we will get is sigma 1 minus sigma 2, we will get it to be 8p by pi d h, where, I'll just explain this, where for a disk, actually let me take this here, for a disk under diametral compression, we have sigma 1 minus sigma 2 is 8p by pi dh. This is from the mechanics of the problem. Similarly, from stress optic law, we know that sigma 1 minus sigma 2 is n f sigma by h. So if we were to equate both of them, we get n f sigma by h is 8p by pi d h, where p is the applied load, d is the diameter of the disk, and h is the specimen thickness. So if I were to solve here, I know that h cancels out. So this gives me f sigma is nothing but 8p by pi d n. In general, in conventional photoelasticity, how they used to calibrate it is, we know from here that 8p by pi, 8 by pi d is a constant. So what is variable here is p and n. As we increase p, n also would naturally increase at the center. So what they used to do is, they will take a disk, they will load it with a p, and they will note the fringe order at the center. This is p and this is n. So this they will be repeating for a number of cases. So p by n. So they will be getting data points like this. Based on every p, they have one corresponding n. So they will be getting a data points like this. So basically what they will do is, they will fit a best fit line, and the slope of that line basically gives us p by n value. Once p by n is given, we just have to multiply it with this constant 8 by pi d, where d is the diameter of this disk, and we will be able to assess what is the f sigma for that particular batch out of which this disk has been cut out. Now with algorithms that with image processing, basically we have tried to make it more statistically robust. Rather than 1 point, we will take some 40 points, because we are able to extract the fringe order at the entire field. Here, in order to extract the fringe order, we would have gone for compensation techniques, but now we need not do that. We have other methodologies like fringe thinning and 3 fringe photoelasticity and phase shifting, using which we will be able to identify what is the fringe order at each and every point in the domain. Once we do that, we will get a number of points. So this same process of calibrating, or rather calibrating the photoelastic material, in other words, the same process of evaluating the fringe order the process of evaluating f sigma has become more statistically stable by us taking some 40 points, and we will be sampling 20 points out of this 40, take 6 values. It is discussed in the lecture how we do this, but for the sake of this problem we just have taken one. Basically we have taken 1 point and we have taken just one load case. So what we have been given is, we have been given just 1 point out of these number of points which we need. So with that background, if I were to substitute, let us say, what is f sigma come out to be? 8p. What is p? It is given in the question as 200 Newton by pi. D, diameter of the disc is 50 mm, and n is not Newton, n is the fringe order. So at the center of the disc, the fringe order at the center of the disc was found to be 1. This is given in the question. Maybe they might have done some compensation technique in order to find that out, but that has not been given. We have been only given the final value, what it is. So we will take it as it is. So it will be 1. So f sigma here comes out to be 8 into 200 by pi into 50 into 1. So we get it as 10.1819 rather Newton per mm per fringe. This is its units. Now generally it is a good practice that when we start doing the experiment, we basically cut out a small disc from that sheet out of which we are going to cut the specimens out, and carry out the f sigma calibration, so that we know for that material and that batch what is the f sigma. Another advantage to this is, let us say that we have cut it, we have done the experiment. After some time we want to repeat the experiment on the same model. With time, if there is any variation in the f sigma, that will also be captured by cutting this disc, because we can always do this calibration again for that disc. So that is one advantage. So this we should keep it in mind in order to calibrate our photoelastic materials. So I take it that this is clear. Okay. So the fringe patterns, I'll move on to the next problem. The fringe patterns for two different cases are given in figures 1 and 2. Identify appropriate scanning direction for fringe skeleton identification using an intensity based algorithm. Enter the value of the angle in degrees with respect to the reference axis shown. Enter only integer values. So basically this says x, this says y, and we have theta. Okay. So let us look at this fringe pattern. Basically what we have here in figure 1 is, these are the fringes. So we are able to see that these are vertical. Hence fringe skeleton is nothing but the center of the fringe. So if I were to draw a line like that, this basically represents the center of that fringe, the skeleton of that fringe. So what will an intensity based algorithm do? Let us say that I take a section like this. Let us say that I consider this box here. Yeah. So let us say I consider this box here. Now this basically has a gradient. If I were to zoom this, it basically has a gradient in and this will keep becoming more and more dark. Rather what I'll do is, I won't explain it like that because I don't have the colors to. If let us say I draw a line like that and plot the intensity. So we know that white color is full intensity and black is almost negligible. So depending on how the fringe gradient is, we will be able to see a dip like this, where this point has the least intensity, meaning that is the darkest point, which represents the actual fringe skeleton, and this happens to be the brightest point, which is this white. So what this intensity based algorithm will do is, it will erode the fringe based on scanning. It will just compare the intensity of the right side and left side pixel and will slowly erode, and this has to be done over multiple cycles, so that the fringe order, the intensity at this pixel, let us say that there is a pixel like this. Let me take it like that. Let me take this. Let us say that this is one pixel, and then we have the adjacent pixel like this, and then we have the adjacent pixel like this. I am just showing you along the graph. That doesn't mean that the pixels are ordering this way. What I am trying to say is, when the image search, the thing intensity is being checked, we will note that the pixel intensity for this second pixel will be less than that of the first. Why? Because this is moving from white to dark. Similarly, the second pixel's intensity will be greater than that of the third, because this almost contains the fringe skeleton where the intensity is negligible. So like this it will perform that, and basically it will erode this. On the first scanning, it will basically erode the first pixel and the last pixel. Then when it comes again, the scanning is done again, it will erode this pixel. So subsequently, as this is done, we will basically at the end of this process, what we will be left with is the fringe skeleton. But this is rather simply said than done, because here we are having an ideal problem where our fringes are absolutely vertical or absolutely horizontal, but this only comes about in very special cases or special problems. This is not always the case. Basically we will be having complex fringe features, so there we will be looking at that how to go about solving that. So basically what we want is, whatever is the intensity variation, we want our scanning to be rather perpendicular to that. So in this case our scanning would have to be along this direction. So scanning for image 1 has to be along the horizontal direction. Similarly, if we were to take the figure 2, here we are able to see that all the fringes are horizontal. So our scanning has to be done in this direction, which is the vertical direction. So I hope this is clear. So what happens when the fringe orders are not exactly horizontal or vertical like this? Not nice patterns, but it is quite complex. In such a case, there has been lot of research on how to go about making algorithms using logics and scanning directions, playing around with them, and to find out which is the most appropriate algorithm for having the maximum fringes resolved as skeletons. So for fringe skeletonization, this question is asking, for fringe skeletonization of a generic image, a global fringe thinning algorithm as shown in figure is found suitable. give the correct logical operators for the logic 1, 2 and 3 as indicated. Enter the logics in the given options below. So what they are asking is basically for horizontal and vertical fringes, if I were to scan in this direction first, if I were to scan in 0 degrees first, what this will give me is a 0 degree scan, a 0 degree scan, will give me, this will give me all fringe skeletons that are vertical, and then it will remove all others that are not vertical. Other word to put it is, it will remove all those that are not vertical. So rather let me write it like that. So 0 degree retains vertical fringes and removes horizontal fringes. Similarly, if I go for a 90 degree scan, so we know that a 90 degree scan basically retains horizontal fringes. A 90 degree scan will retain horizontal fringes and remove vertical fringes. So if I were to, let us say, if I were to put a condition that both of these should be satisfied, then naturally I will not get any output out of this. Whereas if I were to say a condition that either of one should be satisfied, then whatever is not covered in one would get captured in the other. So this is basically, this comes in handy where my fringe direction is some generic direction. I scan it horizontally and I do it vertically. In order to have a double check that that is indeed the fringe point, I need to basically use a OR operator for this. So what we do is basically, either if it is coming in either 0 degree scan or 90 degree scan, we will consider it to be a fringe. We will consider that to be a fringe, and we will go with the OR operator. Similarly, if we go for a 90 degree scan and its complementary 135 degree scan, there also we go for a OR operator. Now both of these would have given fringes which we basically of the same image, these would have scanned and given some fringe skeleton. Now it has been found that when we do an AND operation on these two, this basically gives the highest amount of resolution. And you can also see the lecture for one of the examples where the professor has shown a disc. Basically we have a disc like this, a disc which has fringes like this, and it has been shown after each and every scan, after a 0 degree scan what gets retained, after 90 degree scan what gets retained, same goes for 45 and 135. And he has also shown towards the end, when we make an AND operation on these two, we are able to see that the maximum amount of fringes get resolved and we are able to obtain the fringe skeletons for them. So that is something that has been researched and found, that basically when we have an algorithm like this, it works in order to resolve the maximum amount of fringes for a generic problem. A generic problem meaning the fringe doesn't have any particular direction to meaning the fringes are not necessarily like horizontal and vertical as shown here, but it can be generic, and this has been tested and papers have also been published on this. So for more details you can consider referring the lecture, and there the output of the fringe thinning algorithm is also discussed in detail. So I hope this is clear. So with this, perhaps I'll move on to this question. It says different fringe features associated with isochromatics and isoclinics. Isochromatics and isoclinics. Now what do we know about isochromatics? Isochromatics, we know that sigma 1 minus sigma 2 is equal to some constant. Similarly, for isoclinics, this gives us theta p is constant. So we have some basically we have some features, and what has been asked is different fringe features associated with isochromatics and isoclinics are given. They are named. Excuse me. So these are named. And we need to identify whether the feature belongs to isochromatics or isoclinics. If it belongs to isochromatics, enter A. If it belongs to isochromatics, enter A, and if it belongs to isoclinics, enter B. Is what is given. So the first thing is source. So what do we imply by source? This is the point from where isochromatic fringes emanate, meaning it's almost like a water, it is like a flow. That is why we are trying to correlate this to fluid flow. So from here, when we load the system, we see that the source actually basically the fringe orders appear from here. So this is definitely related to a isochromatic. This is definitely related to isochromatic fringes. A singular point. Now what is a singular point? So let us say that we take a model, let it not be circular, let it be some generic model, and we place it in a polariscope, and we have the light source here, and we have the polarizer and the analyzer crossed. And then as with time, what we do is we rotate this crossed combination in order to find the isoclinics at each and every point. When we see this configuration specially, we might be able to see the isoclinics like this, where this represents the this represents theta equal to 0. Similarly, when we rotate it like that by, let us say, 5 degrees, we might have another set of isoclinics which will be having all theta p equal to 5 degrees. So like this, if we go on doing this, we will be able to map, we will be able to see that the isoclinic basically sweep the entire model. Now another peculiar thing happens is it need not cross at a point like this. This I have shown especially to emphasize a point. So when it happens somewhere at a point where it is not loaded, let us say somewhere in the middle of the domain, we are able to see that many isoclinics basically cross at a point. So what does that imply? At this point, if all the theta p's are crossing, that implies that all the directions are basically principal directions. So what this implies is whatever plane we go to, that represents a principal direction. And what is a principal direction? It is the direction on which the stresses applied on that plane are the principal stresses. In other words, if we have a case where these isoclinics are all crossing at a point which is not loaded, here all the directions are principal stress directions. In another way to say this is all the stresses are principal stresses. So sigma 1 minus sigma 2 is n f sigma by h, we know that. If all the stresses are principal stresses, then sigma 1 minus sigma 2 is 0. If all stresses are principal stresses, then sigma 1 minus sigma 2 is equal to 0, which implies that, or rather I should say, this means sigma 1 is equal to sigma 2, and as a consequence of this, fringe order at that point is 0, because the left hand side goes to 0. So in a model, if we were to conduct this plane polariscope experiment where we try to locate all the isoclinics, and if it so happens that it passes through a point, all the isoclinics pass through a point which is not loaded, they have no directional dependence, meaning they are isotropic, similar in all directions. That is the meaning of isotropic. So that is what has been adopted here. So they are isotropic, and at that point fringe order will be 0. So such points is what is known as an isotropic point. Here the last option. So the isotropic point is related to isoclinics. I jumped an option in order to explain this, just to explain what is the difference between isotropic point and a singular point. Now it will so happen that this phenomena of all the isoclinics passing through a single point will also be observed at the loading point, wherever this thing is loaded. For example, if I take a disk and if I load it, now we generally see that the isoclinic fringes are like this for 0. Then for 30 degrees it will be, in fact let me draw this for 1 or 2 cases. So for 0 degrees the isoclinics will be like that, symmetrically of course. For 30 degree it will be like that, and for 45 it will be more like this. So we are able to see that all the fringe orders, all the isoclinic fringes, they cross at this point where it is loaded. So an isotropic behavior at a point which is loaded signifies that that point is a singular point. So this is also related to isoclinics. So these are basically singular points. These are basically singular points. And then once we saw a source, the opposite of that would be wherever fringe order disappears, that is a sink basically. So here also this is also related to a isochromatic fringe. Now a saddle point, let us see it from the first example. If we look here, I will just remove this. Let's remove this in order to explain. If we see here, now there are 2 fringes like this. If we were to load it more, what we would observe is this will become a fringe and this will become a fringe, and a gap will be generated here. So what we see, that what is a saddle point is basically a fringe, a point where 2 opposite fringes match and then separate out in the opposite direction. So if I were to, or rather in the same example, let me show. This is for a isoclinic this thing. Here if I were to draw the isochromatic fringes for this, for a disc, when I draw the isochromatic fringes, basically I will be initially having fringes like that. Now and then we will have something like this. Let us say that I load more. This is the direction in which P increases. This is P increases. What I will see is these two fringe orders will merge. So this will go something like this, and basically I will have the fringes merging like this. So basically these two became one and there was a separation. So what do we generally mean by saddle? Saddle is a place where we have two opposite curvatures. This is what is called a saddle. So the same terminology has been used here. Basically in one direction if it is concave upwards, in the other direction it will be concave downwards. So that is the basic example for a saddle. Physically and even in multivariable calculus we know what is a saddle point. So a similar parallel has been drawn in terms of our fringe features, which again has to do something with isochromatic fringes. So this is A and this is also A. This is A, and saddle point is also related to the isochromatic fringes. And as for isoclinics we have to enter B. So I would rather enter B rather than writing isoclinics. So I hope this is clear. So based on whatever we have discussed, let us look at this question. The fringe pattern of a ring. Ring is basically we are having the same two annular things subjected to a diametral compression. So this is how the patterns look like, and if you see the lecture, it is shown how these patterns vary as a function of load also. As the load is increased, how these patterns vary, that sort of a video is shown in the lecture. I don't have the video with me, but you can refer the lecture for that. So the fringe pattern of a ring under diametral compression is shown in the figure. Sorry, just a moment. Shown in the figure. Different points are marked in the figure. Enter the correct name for the fringe feature. These features what we discussed earlier. Enter the correct name for the fringe feature which the points represent. Enter, for source you enter, it is just a nomenclature that they are given. For source you enter SO, for sink you enter SI, for a singular point you enter SIP, saddle STP, and isotropic point ISO. This is for just evaluation purpose. Anyway, so let us look at what the points are. Where is point A? Point A is over here. So what happens basically is, if you were to see, I don't have that video, but that if you see the video of the stresses evolving as a function of the load, I would rather suggest it here. Let me write it here. Visit the video of isochromatics as a function of load from lecture. So I think one will be able to appreciate this better if they have a look at that video. Unfortunately, I don't have that with me right now. But anyway, that is why I am mentioning that you please revisit this. So when we see that, what we see is that the fringes evolve and it starts disappearing here. So when we load it more, this fringe basically becomes thinner, and whatever is inside, it disappears, it basically vanishes. So what point A represents is a sink. Point A represents a sink, whereas as we load it, we see that from here and symmetrically on the opposite sides we have fringes emanating. So these basically represents the sources. Point B represents the source. Point B represents the source. Point C and D. Now again, if we see, what will happen is this, we have a point over here, we have this point over here, and then we have sort of a fringe like that. So as there are more fringes emanating from this place, we will just have a fringe become more and more dense here, but this middle point will never vanish essentially. So if it doesn't vanish, it is not a sink, but it is an isotropic point. Essentially, if we see the isoclinic fringe features, we will have all the isoclinics pass through this point, and this is not loaded, so this is essentially an isotropic point where our fringe order is 0. So point C. Similarly on this, and this is a symmetric problem about the vertical. So if we have an isotropic point here, similarly we will also have an isotropic point at D. So we have point C is an isotropic point, and point D is also an isotropic point. Next, what is given is point E. Now since that is loaded there, we can easily conclude let us move on to this question. So the fringe patterns, basically isochromatics corresponding to an angle bracket that was initially shown even in the first question, is subjected to a load on these points. Different points are marked using red, yellow, green and blue colors. What we need to do is identify the fringe order integers, because this is a dark field image, so fringe orders would be integers at the points indicated by these colors. Now at the very starting, for the first problem itself, we have identified this is a free outward corner. This is a free outward corner. I mean, this is a free outward corner. So the fringe order there is 0. So the fringe order at the red point equal to 0. Now this is a continuum. The body is a continuum, and we are looking at one arrangement, perhaps the dark field arrangement, because we are able to see the fringe order 0. So from 0, the fringe gradient increases in this direction. Hence, if this is 0, then naturally yellow would have to be 1. Yellow would have to be fringe order equal to 1. So the yellow would be fringe order 1. Now here basically we are moving, if we see like that, in this direction the fringe gradient basically increases because we are moving towards the load point. So if this is 1, then the next fringe order would have to be 2. Similarly, if this is 1, the yellow is 1, we are able to see that the next fringe here is this. So this is 2. If this is 2, then the next one here would have to be 3, 4 and so on. So from here we can easily conclude that green is nothing but fringe order equal to 2, and the blue here also, here this is fringe order equal to 2, and the blue point is fringe order equal to 3. So green is n equal to 2 and the yellow is n equal to 3. So what we basically need here is a point where a fringe order is known and the fringe gradient direction, which we can assess based on our knowledge of the problem and the mechanics. And if need be, we can also look at some fringe features if they are prominent in order to do the numbering of the fringes. So I take it that this is clear. Okay, so I'll move on to the next question. What it says is, at a point D in a photoelastic material, so we have some problem, not a disk, let us draw it as a generic problem. At some point D, this is point D, the fringe order is found to be 4.25 at D. At D, the fringe order is found to be 4.25 is given, was measured. Okay. The isoclinic parameter at the same point is 35 degrees. So theta P is basically 35 degrees at that point. The material stress fringe value of the model material is 12 Newton per mm per fringe. So material stress fringe value is given by F sigma, which is given to be 12 Newton per mm per fringe. So from this also we can assess that actually the material is epoxy, because for epoxy only we have F sigma near around 12. For polycarbonates around 8, for polyurethane about 0.3 and so on. Okay. So the model materials Young's modulus is 3.275 GPa. So the Young's modulus is given to be 3.275 GPa. And its Poisson's ratio is 0.6. It's 0.6, not 0.6. It cannot be more than 0.5. It is 0.36. So this is given. Now it is said that before application of the loads, the model thickness was 6 mm. H before loads was 6 mm. And after the application of the load, the thickness at D at this point measured by a lateral extensometer was 6.01 mm. So H1 after loading 6.01 mm. So it is 0.01 mm, it has increased. So what is asked is find the principal stress difference. So for principal stress difference, let us invoke the stress optic law. In fact, this we even discussed it in some previous session. When these quantities are given, how will we go about evaluating this? So we know that sigma 1 minus sigma 2 is n F sigma by h, which is n in this problem was 4.25 into f sigma is 12 and the thickness is 6 mm. So basically what we have here is sigma 1 minus sigma 2 is 8.5 MPa. So we have found out the principal stress difference, which has come out to be 8.5 MPa. Okay, so this is 8.5 MPa. Find the normal stress difference sigma xx minus sigma yy, considering that this is in the xy plane. So that is implied actually. This is in the xy plane and out of plane this thing is z, the right hand rule. So sigma x minus sigma y. Okay, so let us say that we have the Morse circle like this, and I am assuming that both the stresses are positive. It need not be so, but in any case it does not bear much consequence to our problem at hand. So this is basically our Morse circle, let us say. So we have here, this is sigma 1 and this is sigma 2. So at some angle theta we have sigma x and sigma y, and this theta at this point is already given to be 35 degrees. It is already given to be 35 degrees. And when we go to Morse circle, we look at 2 theta basically. So what I can do is, I can take a line like that and I will rotate it minus 2 theta p in order to get to where my plane is. So basically when I rotate it by minus 70 degrees, I have got to where my plane is. So at this point I have sigma xx, and if I were to project this in the opposite direction, I will get this to be, sigma yy, and this ordinate, this represents tau xy. This quantity represents tau xy. So this much we know, and this is 2 theta p. Now another information I know is, what is this distance? Sigma 1 and sigma 2. So this is basically equal to 8.5 MPa. From my calculation I have got this. So let me consider a triangle like that. And I will just isolate this triangle. So for the side, this side's length is nothing but sigma 1 minus sigma 2 by 2. So this is sigma 1 minus sigma 2 by 2, which is the radius of the Morse circle, which is equal to 8.5 by 2. This length is nothing but our tau xy. So this is tau xy, and this length is nothing but, if I draw a projection from here, this distance is sigma xx minus sigma yy. From the symmetry, half that distance will be sigma xx minus sigma yy by 2, and I know this angle is nothing but 2 theta p. So this is all the information that I need. So from the triangle, I know sigma 1, or rather I will say cos 2 theta p is nothing but adjacent by hypotenuse, which is sigma xx by sigma yy by 2 divided by sigma 1 minus sigma 2 by 2. This follows that sigma xx minus sigma yy is nothing but sigma 1 minus sigma 2 cos 2 theta p. So this follows that sigma xx minus sigma yy is basically 8.5 cos 2 into 35 degrees, of course, so cos 70. So 8.5 cos 70 degrees is coming to sigma x minus sigma yy is it comes around 2.9091 MPa. So I have got the normal stress difference as 2.91 MPa. So this comes to 2.91 MPa. Very well. Shear stress. Sorry. Just a moment. Yeah. So shear stress, I can just take the other angle. For shear stress for the same triangle. From the triangle, sine 2 theta p is nothing but the opposite side upon the hypotenuse, or tau xy can be written as sigma 1 minus sigma 2 by 2 into sine 2 theta p. So from here it follows that this is, we got this value to be 8.5 by 2 sine of 2 into 35 actually, so that will be 70. So we get tau xy from here as 8.5 by 2 into sine 70. So this comes around 4. This is 4 MPa. Very well. Okay, my screen is not moving. What is the issue? 1 minute, I'll just stop presenting and present again. Seems to be some issue with my yeah, actually I think the screen got stuck here, so I'll just quickly give the explanation. Basically this triangle I have taken it back again, and yeah, what I've done, I've just taken sine of the angle. So sine 2 theta p is tau xy upon sigma x minus sigma y by 2, and from there basically I've just cross multiplied and I have substituted the values in order to get tau xy to be 4 MPa. Okay, so tau xy comes out to be 4 MPa. Now they have asked what is the stress component sigma xx and what is the stress component sigma yy, is what is asked. Okay, so let us look at this. Now for this case, taking plane stress condition, we know that from generalized Hooke's law, we have epsilon z is nothing but sigma z by E minus mu sigma x by E minus mu sigma y by E. This we know. So Ez is given by sigma x minus mu into sigma x plus sigma z minus mu into sigma x plus sigma y whole by E. Now for this case, for plane stress, sigma z is 0. So this follows that epsilon z is nothing but minus mu by E into sigma x plus sigma y, or sigma x plus sigma y is minus E epsilon z by mu. So this we have found. Now at point D, it is given that before loading thickness is 6 mm. After loading, the thickness is given to be 6.01 mm. So what is the out of plane strain? It is nothing but delta z by or rather I shouldn't say delta z, it is basically change in the thickness by the original thickness, which is 6.01 minus 6 by 6.00. So this comes out to be Ez is nothing but 0.01 by 6. This is the out of plane strain. Now this I will just substitute here, and I can get sigma x plus sigma y is nothing but minus E. What is E for this material? E for this material is given over here. E for this material is 3.275 GPa and mu is 0.36 GPa. So if I substitute that, I get sigma x minus sigma y is 3.275 into 10 power 3 GPa by 0.36 into epsilon z, which is 0.01 by 6. So this is what I have. This another equation that I have. So let me call this equation number 1, or rather equation number 2, if that is convenient. And which is equation number 1? I have this as equation number 1. So if I were to take a copy of this, this equation 1, and I have equation 2 like that. So if I were to recast this, these are two equations and two unknowns. So if I try to do it by elimination, I'll just simply do it with the matrix thing. So what I can see here is this into sigma xx. Sigma x and sigma xx are one with the same thing. So I hope there is no confusion there. It's nothing but the right side vector, which is 2.91, and this is minus 3.275 E3 into 0.01 by 0.36 into 6, and here I have 1, minus 1, 1 and 1. So if you open this out, it will give the same equation. So from here I can get sigma xx, sigma yy is nothing but the inverse of this into this vector. So let me see what that comes out to be. 6, 1, 5, 1 minus 1, 1, 6, 2.91, and this is minus 3.275 E3. We can call 3 down. This is minus 15 point. In fact, let me replace this with the actual value. This comes out to be minus 15.162. So this I can inverse into this, comes out to be 6.13. So 6 minus 6.126, and this is minus 9.036. So in fact our assumption initially was that both are positive. However, that we are able to see that that doesn't hold good. In fact, both are compressive in nature. So since both are compressive, ideally my axis should be somewhere here, somewhere over here, so that this sigma x is minus 6 and this sigma y is minus 9. So now it figures, now it makes sense. So I will just change this also to this direction and perhaps move this over here. So this is actually sigma y. Very well. So actual Mohr circle would have been like this. So I hope that is clear. So we have essentially been able to separate out the stresses with our photoelasticity and out of plane displacement measurement. So anyway, with this I have run out of questions. If there are any other questions that you have, I am happy to take them now.
Sir, I have only one question, sir.
Yeah.
See, regarding the thresholding technique.
Okay.
You are converting the image to a binary image.
Yes, sir.
So to get the fringe skeleton,
Yeah.
if we set a very low value of the threshold,
Yeah.
nothing else is required to be done.
Okay. See, basically what you are saying is, if I were to, let us say I have an image where I have fringes, like this, and then now I am doing thresholding for this image. Basically I am this is a grayscale image. I am converting this into a binary image by setting a threshold, and let us say that I set the threshold at 125 or so, let us say halfway, or even not halfway, some chosen value. What you are saying, if I set the threshold as low as possible, it should be able to give me the fringe skeletons. But that would only hold good if the fringe skeletons are of the same width. See, as when you saw here, let me explain it with the example. If we see here, you are able to see that this fringe is comparatively thicker as compared to when we go near the loading point. So, fringes in the low fringe gradient zones are generally wider, whereas fringes in the high gradient zones are very thin, because the gradient is so very high, so the fringes become very thin. So, if you were to set a very low threshold, then you will not get resolution over here. If you set a very high threshold, then you will miss this out. You might be able to get fringe thinned at the high gradient zone, but you will miss what is happening at the low gradient zones. Yeah. Yeah.
The center of the fringe is going to be dark.
Yes.
With respect to the width of the fringe,
Huh.
in the middle we are going to have very low intensity.
But that is in a grayscale image. In a grayscale image, the center of the fringe is bound to be the darkest, which will be absolute black. Whereas as we move away from that fringe skeleton, it will be some sort of grayscale. Now, if you set when you are doing thresholding, basically what you are saying is this entire area is only black, and above that is only white. That is what is binarization, right? So, when you are doing thresholding, basically what it will do is, instead of one line of pixels, it will take one area of pixel and make it black. Whatever is above that, it will make it white. So, only when fringes are of uniform density, uniform thickness, for example, whatever you said, setting a very low threshold and getting fringes will work for this. For such a problem, if you set a very low threshold, you will be getting only basically lines. But for real life problems, because of the variation in the gradients, you will not have fringes of this uniform thickness. That is why this problem comes. Clear, sir? Yeah. Okay. Okay, perhaps if there are no further questions, then we can consider calling it a day. We will see on Monday, on this coming Monday, we will be discussing week 7. Right. Thank you very much. Okay. Yeah. Full disk, I have just taken half portion of it, and this is done using an in-house developed software called DigiPhoto, which is developed at the Digital Photomechanics Lab, IIT Madras, under the authorship of Professor Ramesh, developed by Professor Ramesh. So, let us say that I go for thresholding. Now, presently I have put 0 threshold, so nearly everything is white. So, as I go on increasing the threshold, we are able to see that we are able to get some bands. But at the loading point, we are able to see this is the low fringe gradient zone, whereas that is the high fringe gradient zone. Since the difference in the fringe gradient zone, as I go on increasing the threshold, I am able to see that as I get discernible fringes here, here the resolution becomes very high, whereas here if I were to reduce this, here if I were to get a very less resolution, meaning almost the skeleton if I want to get, I have loss of data at the high stress gradient zone. So, this is the issue with just having a common threshold, and this is why we basically require our fringe thinning methodologies. So, I hope with this you are able to get some clarity about what thinning is and why we need scanning methodologies and the logics, that is clubbing two orthogonal direction scannings and adding them with an AND. So, I suppose you get that now.